Have you ever been inside a huge skyscraper and wondered how on earth it stays perfectly cool in the middle of summer? Well, today, we're going to pull back the ceiling tiles and take a look at the hidden lungs of our buildings, the ductwork. It's kind of like their respiratory system. So, let's dive in.
Yeah, it really does feel like magic, doesn't it? But behind that perfectly controlled temperature, there's this incredible journey happening. So what we're going to do is follow just one little puff of air, all the way from the giant fan probably down in the basement, right up to where you might be sitting. You ready to follow along? All right, so here's our game plan for this little journey. First up, we're going to design the perfect vehicle for our air. Then, we'll map out its route, kind of like a road map. After that, we'll have to deal with some of the challenges, the traffic jams and roadblocks it might face. And finally, we'll make sure that air gets delivered right to its destination.
Okay, so let's get right into it. Section 1. We're starting with the absolute basics, the duct itself. Before we can send air anywhere, we've got to build that perfect vehicle to carry it, right?
The very first thing we have to decide is its shape. And for that, engineers have this term, aspect ratio. Now I know, it sounds super technical, but it's really not. All it is the ratio of the longer side of a rectangular duct to its shorter side. That's it. It's all about getting the dimensions just right for our air's little trip.
So what's the perfect shape? Well, it's a perfect square, an aspect ratio of 1:1. And this is the really cool part. A square duct creates the least amount of friction. That saves a ton of energy over the life of the building. And on top of that, it uses the least amount of sheet metal, which saves money right from the start. Now, a perfect square is the dream, but engineers do have a little bit of wiggle room that can go up to a 4:1 ratio.
Okay, next question. How thick do the walls of the duct need to be? Well, it's pretty simple actually. The bigger the duct, the thicker the metal has to be to keep it from, bending or breaking. Engineers just use a simple chart, just like this one. You find the duct's longest side, let's say it's 36 inches, and boom, the table tells you exactly what thickness or gauge of steel or aluminum you need. Super straightforward, but absolutely critical.
All right, our vehicle is designed. Now for part 2, planning the roadmap. We've got to figure out the absolute best path for our ducts to take as they travel through the whole building.
Look, if you remember only one thing from this whole lesson, please make it this. The most important rule for designing ductwork is just go straight. Seriously, the simplest, most direct route is always the best. Air, just like people, prefers the path of least resistance. It wants to go in a straight line, and fighting that costs a lot of energy and a lot of money.
And you can see the difference so clearly here. When you go straight, you get lower energy bills because the fan just doesn't have to work as hard. You also get lower installation costs because you're not buying all those expensive custom fittings to make a bunch of turns. The bottom line is, going straight is just a total win-win. So when you stick to that go straight rule, you usually end up with one of these 3 main layouts. You've got the spine layout, which is like a central backbone for those long, narrow buildings. Then there's the H pattern. This is the most popular one. It's great for wider buildings. And finally, the loop layout, which is kind of a variation on the H pattern that you'll see in really big multi-story buildings.
And just like a highway needs bridges and supports, ducts need hangers. Otherwise, they just sag all over the place. And yep, you guessed it, there are rules for this too. It's pretty logical. The bigger and heavier the duct, the closer together the hangers need to be. So a small duct might only need support every 8 feet, but a really massive one is going to need a hanger every 4 feet to hold it up.
Okay, so our air is officially on the move, but its journey isn't always a smooth, easy ride. It's going to face some challenges, some obstacles that create resistance. And we're going to talk about 2 big ones, friction and bends.
So here's a really simple but super important rule of physics when it comes to air. The faster you try to shove air through a duct, the more resistance you're going to get. The duct basically pushes back, and that resistance, that's what the main fan has to fight against. But the question is, how much harder does it have to work? The answer is, probably a lot more than you think.
Just take a look at these numbers. This is where things get a little nuts. If you double the speed of the air, the resistance, it doesn't just double. No, it goes up by 4 times. It quadruples. And what if you quadruple the speed? The pressure goes through the roof by a factor of 16.
But wait, here's the real kicker. To overcome that pressure, which quadrupled, remember, the fan has to use 8 times the power. Let that sink in. 8 times. And this is exactly why controlling the speed of the air is one of the most important things for making a building energy efficient. So where is all this energy loss coming from? Well, it breaks down into two main types. First, you have friction losses. Think of this like a constant headwind when you're driving down a long, straight highway. It's always there. Then you have dynamic losses. These are more like the energy you lose making a sharp turn or a sudden lane change. They only happen at the fittings, like at the bends and turns.
So to cut down on those dynamic losses, engineers pay a lot of attention to how they design the turns, which are called elbows. The whole goal is to make the turn as gentle and smooth as possible. See, a nice wide curve lets the air change direction without creating a bunch of chaos and turbulence, and that saves energy at every single turn in the entire system.
Okay, we've built our duct. We've planned its roadmap. Now for the final and maybe most important stage, actually directing the air to its destination. We gotta make sure the right amount of air gets to the right place at exactly the right time. This is all about control.
And the first layer of control is something called zoning. It's actually a really simple idea. You just group rooms together that have similar heating or cooling needs. For instance, maybe all the offices on the sunny side of the building are one zone and all the cooler rooms on the north side are another. It's like creating different climate neighborhoods, and it lets the system be way more efficient and keep everyone comfortable.
So how do you actually control the air going into each of these zones? You use something called dampers. The easiest way to think about them is as the traffic controllers for the whole ductwork system. They're basically just little valves inside the ducts that can open and close to manage the flow of air.
And there are basically two main kinds of dampers you need to know about. First, there's a control damper. This one is like a faucet for air. It's opening and closing all day long, adjusting the volume of air going into a room. Then you have a balancing damper, and its job is totally different. Its goal is to regulate pressure. A technician will set this one time, lock it in place, and that keeps the whole system in balance. It's what stops you from getting those annoying drafts or doors slamming shut. And finally, we have to talk about some really important dampers that are all about safety. Fire dampers have this little link inside that's designed to melt if it gets too hot. When it melts, bam, the damper slams shut and stops fire from spreading through the ducts. Smoke dampers work the same way, but they're triggered by a smoke detector. These things are absolutely critical lifesavers because they stop a fire from spreading through the building's own lungs. And with that, our little journey through the ductwork comes to an end. We've seen how these hidden networks really are like the respiratory system of a building, carefully designed to help it breathe. So that leaves me with one last question for you to think about. If the ductwork is a building's lungs, what other systems act like the body's other organs? What about the electrical wiring or the plumbing? What part of the body are they? It's a cool way to think about the buildings we live and work in every single day.